just hold on, we're still early. Jeffrey, your job. Sarah, you have got to speak loud enough so that Jeffrey can easily hear you, okay? If not, I want Jeffrey to let us know, okay? Because this is part of doing this. And actually, so one of the reasons why I think doing presentations is such a good thing is that, well, for example, when I was a kid and took piano lessons, I pretty much hid it. I didn't want anybody to really hear me, and and it just reinforced my shyness and everything. On the other hand, our youngest son, who is a percussionist, so I took him, when he was old enough to start piano lessons. And one of the things that the piano teacher did was that once a week, all the kids had to sit around together, and essentially, even as little kids, were doing peer evaluation. And so he developed, without, sort of the crazy fears that I had. And so that is one of the reasons why, we've got this nice, safe space, and I want you to practice, being verbal, okay? Okay, so I'm not picking on you. This is for your own good, Sarah. So, okay, now before I turn her loose, do you have any questions or concerns, worries, or anything? Okay, yes.
I have a presentation redo. I didn't realize it was a safe space when I was presenting. I was terrified of your questions.
I got one on Wednesday.
Oh, okay, I can do that one.
Okay, so. Okay, with that, I know that Sarah is anxious, and she's actually, and I know that everybody has done a lot of work on these, but Sarah has been asking lots of good questions throughout. So she's got lots of good stuff to share with you. So, Sarah.
Okay, hi everyone. So my project is about a resistant analysis of hospital wastewater in Missouri. So wastewater in general contains a lot of chemical, physical, and biological contaminants, and then the wastewater gets through the wastewater treatment plants to get treated, and after it's treated, it's discharged into the environment. So in general, we tend to have two types of wastewater treatment plants. We have the municipal wastewater treatment plants, which receives wastewater from industries, from companies, from facilities, and from hospitals. And then we have the domestic wastewater treatment plants, which receives wastewater from households. So the municipal wastewater treatment plants act as a main point source of exposing the environment to antibiotic resistant genes. And once discharged into the environment, antibiotic resistant genes are transported to the environment and chains, or the humans can get directly exposed to the antibiotic resistant genes through water drinking. So the wastewater treatment plants receive a wide range of antimicrobial agents such as antibiotics, biocides, pharmaceutical contaminants, and then all these contaminants create an enrichment condition for antibiotic resistant genes and act as selective pressure, allowing the genes to resist even after wastewater treatment plants. So my first approach to this problem was to analyze what are the types of antibiotic resistant genes that are most commonly present in wastewater. And then after doing a literature review, I came up with this table. And then by looking at this table, I realized that most of the antibiotic-resistant bacteria present in wastewater treatment plants are clinically relevant antibiotic-resistant bacteria. So clinically relevant antibiotic-resistant bacteria means that we are essentially looking at two main sources, hospitals or households. And given the fact that I'm looking at municipal wastewater treatment plants, I decided to select or study hospitals. So hospital wastewater harbors a multitude of antibiotic-resistant genes, and it has been demonstrated that some of those genes resist even after the wastewater gets treated through the wastewater treatment plants. And this reflects the ineffectiveness of wastewater treatment plants in targeting and eliminating most antibiotic-resistant genes originating from hospitals, and that wastewater treatment plants contribute to the spread of those genes into the environment. So the World Health Organization emphasized the problem of the spread of antibiotic-resistant genes, saying that without urgent coordinated action, the world is heading towards a post-antibiotic era in which common infections and minor injuries, which have been treatable for decades, can once again appear. So the first thing that happens is that we have a lot of antibiotic-resistant genes emerging at the hospital due to the consumption of antibiotics. And then after that, the antibiotic-resistant genes as well as other contaminants get discarded into the wastewater. And then the hospital wastewater acts as the main source of the dissemination of antibiotic-resistant genes into the environment, and then the presence of those genes in the environment and water, soil, and sediment pose a major threat to organisms in the environment and communities, threatening the overall environmental sustainability and well-being. So first, this is a schematic representation of the sources and the pathways of antibiotic-resistant genes from the hospital wastewater to the wastewater treatment plants and to the environment. So first, we have the hospital here. We have a lot of things that lead to the emergence of antibiotic-resistant genes, including the medical unit, the labs, and the surgical units. And then the antibiotic-resistant genes, as well as other contaminants, are discarded into the hospital wastewater, which contains heavy metals, chemical and pharmaceuticals, as well as microbial contamination. And then the wastewater gets discharged into the municipal wastewater treatment plants. So the first step we have here is the primary treatment, which is the removal of physical or insoluble objects from the wastewater. And then we have the secondary treatment, which is also referred to as the biological treatment, which is the removal of organic contaminants from the water. One of the end products of the secondary treatment is sludge. And then after that, we have the last step, which is the tertiary treatment, which is the removal of inorganic contaminants from the water, and this is where we see a lot of elimination of antibiotic resistance. So it has been observed that a lot of these heavy metals and the chemical contaminants get effectively refused through the municipal wastewater treatment plants. But it was observed that a lot of antibiotic-resistant genes do persist here even after the wastewater gets treated. So this demonstrates the ineffectiveness of municipal wastewater treatment plants to target or to eliminate antibiotic-resistant genes. And then these antibiotic-resistant genes get spread into the environment, aquatic environment, and then into the livestock, and from livestock to human beings, and from human beings back to the hospital. So my plan here is to do a resistome analysis. So a resistome analysis is a metagenomic study where we identify and characterize antibiotic-resistant genes. So I'm planning to do a resistome analysis at this point before the wastewater gets discharged into municipal wastewater treatment. And then I'm going to do another resistome analysis at this point to analyze antibiotic-resistant genes that persisted after wastewater treatment plants. And then I'm going to do a comparative study or analysis to compare or identify the types of antibiotic-resistant genes that persisted after wastewater treatment. So most of the previous related studies have analyzed this problem on a very narrow scale, where they only analyzed about 3 or 4 hospitals. But from my perspective, a problem which is as serious as this one needs to be analyzed on a case-by-case basis on a large scale. And for that reason, I decided to do this study on a large scale in a state which is as complex as the state of Missouri, and then analyze about 64 hospitals to get a large scale of serious problems. So the objective of this research work is to evaluate the efficiency of conventional wastewater treatment plants in removing antibiotic-resistant genes from the hospital wastewaters of 64 hospitals in the state of Missouri, and then to identify the types and the quantity of antibiotic-resistant genes that persist after wastewater treatment. And antibiotic-resistant genes will be identified based on the resistome analysis of hospital wastewater before it's treated and after it's discharged from the wastewater treatment. So the amount of antibiotic-resistant genes will be quantified to indicate the potential source and the extension or the extent of antibiotic-resistant dissemination in wastewater treatment plants from hospital analysis. So I'm going to skip this slide for now. So one hypothesis are that a resistant analysis of the water effluent from 64 hospitals across Missouri would indicate a wide range of antibiotic-resistant genes present in the hospital wastewater effluent before it is discharged into the wastewater treatment plants. And then following the discharge of the water into the wastewater treatment plants, a resistant analysis of the water effluent would indicate a wide range of antibiotic-resistant genes originating from the hospital's resistance after treatment. And then the wastewater treatment plants will reduce some of the analyzed antibiotic-resistant genes, however, a few amounts of the resistant genes will resist. So the genes that resist are the ones that are most likely enriched for the environmental conditions and stressors present in municipal wastewater treatment plants. And even though the antibiotic-resistant gene profiles will vary from one hospital to another, this variation will not be large. And that most of the genes that resisted through wastewater treatment plants will be common among all the hospital analyses. So the resistant genes identified through the resistant analysis will be among those that pose a critical threat to the environment. So this is a very famous quote for the politician Donald Rumsfeld, and I really find this quote very interesting, and I think that it highly applies to the case of unidentified antibiotic resistance. So he said, there are known knowns, there are things that we know that we know. So the known knowns here is tracking the genes and the pathogens that we have already identified and have an idea about. So he said that there are known unknowns, that is to say, there are things that we now know that we do not know. So the known unknowns would be analyzing the genes that we do not normally track, which like variants of known genes. But there are also unknown unknowns. There are things that we do not know we don't know. So the unknown unknowns would be the emerging threats, such as novel antibiotic-resistant pathogens. So this is a basic overview of the metagenomic analysis. So in my report, I won't go more detail on how long to perform each and step of them. So the first thing we do is water sampling. We take some samples of water, and then we have processing DNA for metagenome, which is DNA extraction. And then we have the 16S ribosomal RNA gene amplification and qPCR, and then sequencing. So the DNA will be sequenced using the Illumina Hi-647, whereas the 16S ribosomal RNA will be sequenced using an Illumina Hi-6. And then after I get my results, I'm going to compare them with databases doing bioinformatics. So the information obtained from the DNA sequencing usually gives information about the types and phylogenies of antibiotic-resistant genes and antibiotic gene relations. Whereas the information coming from sequencing the 16 and S ribosomal RNA gives more information about the abundance of the antibiotic-resistant genes. So the expected outcomes is that a wide diversity of antibiotic-resistant genes will be present in all the 64 hospital wastewater before being discharged into wastewater treatment plants. There will be some variations in the resistant genes profiles in hospital wastewater by different hospital analyzed, but this variation will not be statistically significant. And it is expected that wastewater treatment plants will eliminate some of the antibiotic-resistant genes. However, some antibiotic-resistant genes will be present in the treated water effluent of the wastewater treatment plants compared to the resistant genes in untreated hospital wastewater. So those antibiotic-resistant genes that will be present after wastewater treatment plants will be classified as resistant genes and are expected to be the ones that confer resistance to a variety of different types of antibiotics and pose a major threat to the environment. So a summary of the persistent antibiotic-resistant genes will be provided and compared among the hospitals, and it's expected that the resistant genes will not vary greatly among them. So the significance of this project is to identify the potential risk of these persistent antibiotic-resistant genes to the environmental sustainability and well-being, and to inform risk assessment and allow policymakers to promote resistance to illnesses and prevent the spread of antibiotic-resistant genes in the environment, and to implement preventive measures of antibiotic resistance in wastewater treatment plants, which is considered a rapid response strategy and clinical practice. So future direction would be identifying the hotspots of disseminating antibiotic-resistant genes into the environment through wastewater treatment plants. So in this project, I focused on hospitals, but in the future projects, we would analyze hospitals. Some new effective wastewater treatment strategies that target antibiotic-resistant genes and wastewater treatment plants, and this was actually my initial proposal for this MSF, which is to implement or design a new treatment method. But given that this is not an data science engineering class, I decided to do resistant analysis, which is, from my point of view, is even more important because we really need to understand and analyze where the problem is coming from before we could design a new treatment method for a solution. So another direction for this study is to apply resistant analysis to the field, which means that we could also perform the same study on like different states, not specifically the state compared to like a
Got 2 minutes.
So actually, one would argue and say that Missouri is one of the states, I think the U.S. in general, that has a conventional wastewater treatment plant. So it does not incorporate any advanced technologies into this plant. So do you think that incorporating advanced technologies, at least the current ones that we have, would help reduce or eliminate antibiotic resistance? So to answer that question, I did a literature review on all the current technological methods that we have right now that has been incorporated into wastewater treatment. And then I looked at the mechanism by which they target antibiotic genes, and I found that even if we incorporated any advanced technologies, we are not essentially targeting antibiotic resistant genes, which means that even all the current technological methods that we have now are considered ineffective in reducing antibiotic resistance. So I think that we really need to implement a new method in wastewater treatment plants that target antibiotic resistant genes. And if I were to incorporate this new design, I would not incorporate it in wastewater treatment plants. I would certainly evaluate whether or not it's effective in reducing antibiotic resistant genes. If it was found to be effective, I'm not going to incorporate it in wastewater treatment plants. I'm going to incorporate it inside the hospital solution itself. So that the water is here inside the hospital before it's even discharged into the wastewater.
The 46 hospitals. I have a couple. Oh, okay, 64. That doesn't include walk-in clinics as well, correct? Okay, and then what were your thoughts on, like, we'll take St. Louis, the 11 miles between Alton, Missouri hospital and the St. Louis hospital? I mean, they're pretty close, like the proximity when you talk about state lines. There could be a possible, they could have a shared water system. They could, I'm just kind of curious on what your thoughts were on how to try to either address it or.
So I'm trying to get like a big picture on all the types of antibiotics that are present. So like I stated in my expected outcomes, I don't expect to see a lot of variation with antibiotic resistance. So that can be very, very challenging.
Are you saying that they might feed to the same wastewater system?
Have you considered the of rural hospitals like the city? Yes, so I'm going to actually select 63 hospitals and 39 of them in the same.
So would another expected outcome potentially be that in these urban environments where you have hospitals that share the same wastewater treatment plants, that you might have higher quantities and larger diversity of the antibiotic resistant present after the tertiary treatment, but that'll be something that should be possibly after the expected outcomes then.
Most plants are those at about 40 and 40
For fact, or it's something else. Say, oh, it's-
So what would be that? Questions. So when you're collecting the water samples and everything, now one of the things to also take into account, the reason why antibiotic resistant genes spread so easily is that you have the presence of plasmids. And so you typically don't find antibiotic resistant genes on the chromosome per se, but on these plasmids. So one of the things that you might want to think about as you're writing up your experimental design is how to distinguish between chromosomal versus plasmid DNA, so you can sort of track that. So that's just a comment.
So you're talking about the movie medicines? It's not necessarily said that you have to do like transposable
Well, the transposons would enable the genes to spread around. So transposons are their own set of genes. So, but yeah, but especially when you're thinking about the antibiotics on these plasmids, they're usually kept within what's considered a cassette. And then cassettes are flat or have at their ends possibly these transposons. So that introduces a whole nother thing, which I don't recommend you going into for this particular project, but good thing to maybe follow up on later. Let's see, my other question. So when you talk about the primary treatment and secondary treatment and everything, and essentially what you're saying is that that's going to select for certain types of antibiotic resistant genes. So what would be the antibiotic resistant genes that you think would end up essentially enhanced at the end of this process? And what would be the selection pressure that would lead to that? Okay, so when you're making statements and all, you need to provide reasons to back it up. Okay, and then you were also talking at the very end about other potential hotspots. One of the hotspots that we've actually studied in my own lab is concentrated animal feed operations, CAFOs. And those are another large impact or contributor to antibiotic resistance in the environment. So if you can sort of expand on what these potential hotspots. Okay. Yeah.
Would you consider pre-treatment processes for hospitals? It's required by the FDA for hospitals to have like some kind of pre-treatment, so
So the thing with pre-treatment, we also consider the primary treatment. The primary treatment
it's slightly different than
so this would be, we think that there
contamination, which could cause fluoridation comes out pre-treatment is like some kind of like addition, so like that is attached to the hospital and not at all wastewater treatment plant. Like wastewater treatment plant is like separate, and so the hospital has to have pre-treatment on site. If that makes sense.
So the virus is the analysis at this point would incorporate water after it's treated. But I don't think we're very confident in who
I think it's different hospitals. You can find out which hospitals have pre-treatment.
I'm comfortable. I don't look at you. That's
Never actually.
okay, so I'm gonna show you real quick. So this button here. So this button there. And this button there has the slide and has this goes backwards. This one didn't go on the screen. Oh yeah, so but don't freak if that happens. Okay. I've seen so many freakers do that. It's like, okay, Laura.
Okay. Alright, so this feels like very powerful, but
It's not, it's just a dumb piece of glass.
hi, my name's Laura. I did my research proposal on the use of indexes and remote sensing to examine the impacts of biocrust and rotational grazing on the high-risk erosion areas of Iowa. So, no, that picture's not of Iowa. Sorry. A little bit of background for us all to just like consider. So biocrust existence, of course, that we've covered in class is important for the retention of soil and the overall health and makeup of the soil environment. We know that well-developed biocrust can protect the soil from water erosion and also wind erosion. And then something that we didn't cover in class, but something that's incorporated into my proposal is ArcGIS, which is a really powerful tool for visualization, and you can take different data sets and put them in. More on that later. And then another thing is that when we use paddocked areas for cattle farming, it allows the livestock to focus on one area for a limited time, so the grazing patterns are different than just free range grazing, which will also affect like the soil and soil environment. Some more background specifically, so damage to biocrust due to livestock trampling is proportional to the intensity of impact. So I can kind of correlate this to you guys as like the size of the animal, the stocking rate of the animals. So if there's a lot of areas in one, or a lot of animals in one area, the stocking rate is higher. And then distance to water sources. So our water sources are going to be more damaged, more trampled, as you can kind of see down here. And then also the amount of time the animals are allowed to graze. So that's correlated with rotational grazing as well. So it's unclear if we just removed all of the cattle in one area, if the biocrust would actually recover or not, because there's just so many factors. But we do know that areas, of course, near these watering holes have increased damage. So if we removed animals from the critically damaged areas, then it would help them. So if cattle are allowed to be selective on a field, so if there's a big field and they're just allowed to kind of freely roam, they're going to choose areas where they like really like that food, and they're going to just eat that down to like the bare grass. And then there will be completely different areas that aren't touched at all. So it can cause more damage in certain areas than others. So paddock areas can help that. More specifics later. And then when soils are dry, that's another season where biocrusts are essentially more damaged because of the disturbance. So just quickly, a quick review over what biocrusts are, because we learned about them pretty early on. But they're made of like these 4 different things, and I guess bryophytes are mosses. So you can kind of see in this picture here, just a quick reminder that the biocrusts intertwine with the soil particles and they release polysaccharide, and it creates like a structure that holds the soil together and down, basically. Also with different roots and filaments kind of like grabbing onto it. So why Iowa? So we had the guest, I guess semi-guest lecture, Dr. Joe, and she kind of went over this, but if you didn't watch it, so Iowa's a humid continental climate, similar to Missouri, which is characterized by humid summers and are very warm with cold, dry winters. And then a lot of our rainfall is in the summer, which also means that a lot of our erosion is in that early spring de-thaw and then rain in the summer. And then Iowa provides a lot of our food. It's kind of a massive agricultural area. And so the 2 main areas that you can see here, the purple and the red, are where we've had the largest impacts of soil erosion in Iowa in the last 8 years. 20 plus tons per acre were eroded in 730 townships, which townships are like established towns and the rural area around them. And then 100 tons per acre in 61 townships in Iowa, which is a lot of soil. So this means that due to compounding factors like global warming, overtilling, and then non-rotational pasture practices, so we're able to, like, animals will degrade those areas really quickly near the watering holes. Those all lead to increased erosion. So just quickly, ArcGIS. So this is what it looks like when you like open it up on your computer. So you can take images and remotely sense data, put them into like a map-like surface, and then you can use different tools to organize it, work with it, compare it, and you can like overlay different data sets on top of each other. So a couple just like vocab words that I'll mention later, so I thought I'd explain them. So raster is any pixelated data set that has a value and a geographical location associated with it. And an NDVI index, this is an indicator of vegetation greenness. So it takes 2 different bands. So these are like bands of light that are sensed with remote sensing, which is like a satellite. So satellite senses it, takes like a picture. You just think of a picture like a raster. And then you can use this like raster and look at the different colors, basically, colors of light, and then also the light, well, the energy that we can't see. And you can compare them to make different images. So like, more of this later. So who cares about this project? So of course farmers are at the center and the purpose, because they're the ones directly impacted by any positive or negative outcomes from the research. So the largest commodities in Iowa happen to be corn, hogs, and soybeans, which does not include cattle. But cattle are kind of how I talked about earlier. They have the most impact per like stomp, basically. So per stomp around watering sources, it's pretty critical. And there's also other research that has been done on cattle with remote sensing and biocrusts. So to justify the additional cost of establishing a paddock area with fencing and water sources, it's important to kind of provide proof to the farmers, because that's additional cost, of course. And then this proof has to find a middle ground between the maintenance and the productivity. So this is kind of huge. Paddocks were not used. So like I'm a 5th generation farmer, and like we don't even have one. And paddocks is basically where you move the animals from small sections quite frequently into new sections, so that they only have enough time basically to not be choosy. So they go and they eat all of the area versus just different spots. And each one has their own water source, of course. And then it basically helps conserve your plant life, and also like your soil is has more health. So we know this, but this comes with a lot of like uncertainty. So farmers have to pay for all of these fencing and water sources. So we need to be able to provide enough evidence to show the impact. So, for instance, like telling them that grazing in the early wet season has shown to be less impactful on the crust cover than in the late winter spring grazing, that's something that they can be like, oh, so if I have this critical area where my biocrust and my soil layers are like not existing or like struggling, then I cannot graze in the early wet season in that area. And they can directly take that. So if we have further understandings, we can provide this tangible evidence on how it can positively affect farming. So my hypotheses. So the overall hypothesis is to establish a connection between cattle circulation and the increase in healthy biocrust. This also has to do with soil erosion because they're just correlated. So compare land areas that utilize varying degrees of rotational farming practices versus areas that don't. So areas that have that kind of pattern we seen on the last slide versus areas that don't. Create an NDVI index using the Landsat data within our GIS, and then when we have that index, the data, we can remotely sense where biocrusts are likely to be formed using these two different indexes. So, to explain it a little bit more, so rotational cattle farming practices, we'll have to basically survey it. So you'll survey the points on the landscape, so like a map, create a map where there is rotational cattle farming happening in areas where there are not. And then you'll, over that same area, you get Landsat ETM Plus data for that area. So the Landsat ETM Plus data that you can see over here, these are the bands of color that are captured when we get data from this satellite source. And this satellite source provides, you choose ETM Plus because it also gives us thermal remote sensing data. I'm usually this over illumination, so you can see these band 6. So utilizing both the normalized difference vegetation index and the thermal crust index. This index has been around for a long time, the NDVI. It basically gives us planet health dimension. And then the thermal crust index was specifically created to look at biocrust from a thermal perspective with the Landsat ETM. So with those two indexes, we'll compare the different wavelengths, and then the two bands that are typically used for NDVI is the red band right here because it'll absorb chlorophyll pigment, so vegetation, and then the near infrared band that has high reflectivity. So then we can get images that indicate areas of biocrust. So we'll choose multiple farms from various degrees of paddock, and we'll also have, like, so for instance, we could do like this region right here, and then we could find areas that have lots of high erosion and areas that don't, and then areas that have paddock and areas that don't. So then we'll rank them based off the degree of cattle grazing. When I say cattle grazing, kind of what I meant, if they're allowed to continually graze, they'll break down all the biological material, and the roots won't be very deep. It'll look like this, very sparse, lots of like non-vegetation land cover. And then if they're allowed to just really graze, it'll be like spots with this and spots with this. But somewhere in the middle here is where the rotational grazing kind of is, like the plant life is able to like remain healthy. So there will be a difference. And then it's possible that once we add Landsat data rasters, so the rasters will cover, so like if we pick this area, they might cover like half of it and then cover another half, and we'll have to mosaic or merge, blend them together to make this green, so that we do computations. So we can load in, literally take this image. We can also kind of geographically, like just like throw it on the map as well, and we can see all of the Landsat satellite data, the areas that we're looking at with rotational farming, and this image all together in our GIS. So if we use the two different indexes, you can kind of, I just wanted you guys to take away like what an index actually does. So if you look over here, this is the NDVI being used in a place southeast of the capital of Germany, Berlin. So they use multi-temporal 16 data, which is just another satellite data set. And this is in the wet conditions and the dry conditions. As you can see, there's like this band of orange and this band of darker orange. So those are like different values of contrasting colors. So like the satellite sees different colors. So like when you turn on certain bands, these are different. This area is different than this area. So extremely low or negative values represent no vegetation at all. Very low values are little to no vegetation, so like bare soil, like kind of the brown color. And then moderate values are like shrubs, and then high values are like forested areas. So what they did in this study was they were able to look at all these different areas, and they were trying to determine what the land cover would be. So would it be bare soil, bioswale crust, or trees? And then they also had grass. That was gray-haired grass, so I guess it was more on the next slide. But so the equation that you put into in the index, you guys probably aren't interested in, but this is where we like contrast the bands. It's like an equation. After we've run the indexes, this we can view and compute the similarities between, in our study, you can look at where the major losses of soil have been. So you saw that map where Iowa had lost most of the erosion. And then also the areas where rotational power forming has happened, and the areas of high erosion. Here, like they've done in a study before, this was when they actually tried to designate certain areas as certain types of land cover. So this is bare soil. So the probability that this would be classified as bare soil is really high right here. So all of that is just like a bare strip. And that correlates with what they found when they were looking for other types of land cover. So like the bioswale crust, this is kind of isolated to like these lands, and then grass is isolated to over here. And then like with trees, they have like a forested area here. So we correlate, like they kind of all go together. So if you fit all of these different areas of land cover, they would cover the entire area of the study area. But they were able to separate the bioswale crust out from the other land use, which is kind of that's what we're looking for as well. So expected results. So we're expecting that the indexes will confirm that areas where rotational farming is happening, where they're moving around the cattle so that they're not destroying just different, like one area all the time. There will be more healthy biocrust than areas where that's not happening, and they're kind of just able to go destructo mode like everywhere they want. So then we'll also be able to confirm that where there is significantly more biocrust, there is decreased erosion in the last 8 areas mentioned earlier, or 8 years mentioned earlier, than when there's areas without biocrust. So basically just confirming what we already know that biocrust can do. So this is the 2 indexes that we'll be using. So like those maps you saw earlier, just kind of put those together in your head with these 2 indexes. Because the studies that have previously been done, and the studies that I've looked at, are done in semi-arid, or arid and semi-arid regions, we're not exactly sure how the different soil types and like the climate will just be different. So by using both of these indexes, yes, this thermal crust index worked really well in arid and semi-arid regions, but also using like NUBI will kind of confirm and then correlate the areas together to make sure we're looking at the right stuff for Iowa and not in arid regions. So, and then being able to showcase the consistent damaging of biocrust with heavy use of cattle is a major contribution to soil loss. But beyond that, being able to distinguish that it's not just cattle, like cattle are the problem, like rotational farming using paddocks is a practice that could actually lead to healthier biocrust in general, rather than just being like, get rid of all of them. So having this answer is also good. So the conclusion will be that we can have the comparisons of where farmers have already put in paddocks and where they have not, and then also understand how the biocrusts are developing because of that. Understanding the impacts of rotational farming. This information can also promote further research. For instance, I kind of was thinking like if I was going to do further research into this, I would probably have an environmental microbiologist on my team rather than a geological engineer. So that would be where they could take that up. And then creating education on how to help cattle farmers utilize rotation farming. Education already exists, but adding in the biocrust aspect of health of soil. So right now it's like plant health is kind of pushed. That's why rotational farming is implemented. But biocrust health could also be another reason for that push. And then this last kind of point is kind of interesting. So I don't know how many of you guys are familiar with the Farm Bill, but the Farm Bill basically tells us guidelines for what we can and can't do for farming. So it governs an array of agriculture and food programs. So for instance, when I worked with the Department of Agriculture, when we did stuff for the Farm Bill, the Farm Bill is kind of like the big name, and then under it, there's different programs that have money that the farmers can use to improve their lands. So when I worked with them, a lot of what we were doing to improve their lands was terracing, which terracing is basically creating bumps in the landscape so that erosion doesn't happen as quickly and as swiftly. It kind of makes the water move differently. So for instance, if we basically can like showcase how important biosoil, kind of how Dr. Joe said, like biological soil crusts are super important and they can also help counteract erosion. That can also go into this because you have that money that when they're improving their lands, they can establish paddocking as a way to help biosoil crust form. So that's how another push for how this could be implemented in actual farming. Because if you take this to a farmer and be like, yeah, spend $20,000 to $30,000 on deep fencing and watering just because you want to improve your land, they're gonna be like, why? Why would I improve my land like that? And where is this money gonna come from? And so this could be a big thing if they ever ride a new one. So, yeah, those are some of my questions. Thank you. Yes, I need questions so that I can write my paper.
So it looks like you already have an index selected in mind for the soil crusts. Have you considered like the length of your sampling times and the frequency of them? Because NDVI and those other things can be severely skewed by clouds and other things of that nature. So have you considered how long you are selecting those data sets for?
So essentially like the aim is in those past 10 years when we have that erosion data. So, or in the last like 8 years from like 2002 to 2010. But if you have to like, obviously we have to pull in, so like land uses changes quickly, like from decade to decade. So pulling in satellite data from earlier on or from later, so like now like 2020 data or 2002 data, or 2020 data from 2002 data, the land use might not be the same. For instance, like that cattle farm could have gone out of business. So there's definitely some unknown variables in that because the land use could change. But I would say essentially we want to cover that 10 years, and then if we have to go, so like basically what Josh is asking is like, so when the satellite passes the Earth, sometimes its view is skewed and like it can't see because of clouds and like just other things going on. So if I had to pull from a different year because there's no clouds for that year, that's something that could very well happen.
It's more of like, if you take a data set from this, you take it for a day, a week, a month.
Oh, you're asking me like that?
Yes, because when I did something with NDVI,
Alright.
when I took it for a month, it was a mess, but when I took it for a day and a half day, it improved my ability to do this, but it also drastically increased the amount of time I had to spend processing data because of the increased number of data sets and more with.
Yeah, so I would probably, since I have unlimited time and unlimited budget, I can theoretically pull as many days as I want. I could do like thousands of days, but realistically, depending on how many people you have working on this, like I think I could probably, like I think my computer could probably run like every day for like a month, and it would be working really hard. So it would just kind of depend. That is something. Yeah.
Have you considered the different soil types and how that might impact conservation and erosion for Iowa?
Yeah, so you mean different soil types within Iowa?
Yeah, like
Or-
ABC or
Yeah,